Hello. So the direction part of the lab is now done with Usha. My name is Dave Reed. I'm the academic supervisor for the laboratory. So we're now going to do a triaxial test. The triaxial test is actually probably the most fundamental type of soil test you can do in terms of establishing things like shear strength and undrained shear strength, friction angle, those kind of things. So we're going to go through how that type of test is done. We're going to use the first material we're going to test, or the only material I'm going to show you how to test, is a sand. It's very similar to the 1630 sand that you previously used for your index testing, or some of your index testing. So this is the sand here. It's a relatively coarse sand. It's actually from a tailings dam in Canada. We're going to prepare a sample with 8 layers of equal size and mass using this tamping device that allows us to tamp the material into the triaxial mold in those layers. The triaxial test is carried out in a cylindrical specimen. Now we need to then prepare the material into the cylindrical specimen that we can then test. The fact that a triaxial has got a circular cross-section enables us to have some advantages in terms of how the stresses are applied to it. So that's what's called an axisymmetric situation. First of all, we take a vacuum pump. So this here is a vacuum pump. It's a simple device that allows us to apply vacuum to this tube. We then use that vacuum to pull the membrane against the walls of the split mold. The split mold is this device here. This is a type of cylindrical mold which has a slot in it, so we can take it apart after we prepare the sample. So that vacuum pump is pulling this membrane against the walls, because the membrane without the vacuum won't actually pull tightly against the walls. That way we can prepare a sample and have it be the right cylinder shape. Because we need the sample to be a very regular, right cylinder. So that's why this vacuum pump's on. It'll be off soon and then we can talk more about what we're doing. So the next step is, when we put the first layer in, and we spread it around, we take this tamping rod, which we've measured, so we know that that is the correct distance for the first layer. And you can see the first layers in place. Okay, that's layer 1. Then we're going to put some slight little marks to prevent there being a rough, smooth interface between the layers. Then we're going to take layer number 2. So now that height's been measured to be the height of the second layer. So we've now prepared the sample. We've prepared all the layers in the split hole. I'll let you take a quick look at the top of it. Now we need to put the top pattern on top of that sample. Get lower in grease. Then we turn that pump off, which is making this video probably harder to hear for you back home. Just put the O-rings on the top. It's always important to put these on because if you forget, and you connect this, you can't get them on anymore, which is a bit of a pain. Okay, so this sample is now ready to be inserted into the triaxial. It's actually got a modular base so that we can prepare things on the countertop and then bring them over to the triaxial cell, like that. We need to connect these drainage lines, because these drainage lines here are the ones that go to the external parts of the cell. These are what we're able to control what's going on with the sample in terms of flushing or consolidation. So we need to take these drainage valves and connect them to the other ones. So there's a bit of a game here of getting this oriented so that the wires don't get in the way too much. That's the bottom connected, and this is the top connected. Now we need to apply a very small suction to the sample so that when we take away this split mold, it won't fall over, because it's not under any stress right now, and it's very loose the way I tamped it. So I want to put just a very small amount of stress on it. Use the same vacuum pump. Different size plastic tubing is very helpful. Bridge these different sizes. So now this vacuum pump is connected to the top of the sample, not the bottom, because the piezometer that measures pore pressure inside the sample is at the bottom. We're going to use that to track how much negative pressure or suction we apply to the sample in this process. Because we don't want to because this pump will pull a suction of about negative 80 kPa. We don't really want to apply that much to the sample because that might be more than we later want to use for testing. So we don't want to apply a very small suction of about negative 20. In order to track that, we're going to use the same software suite. In this case, the pore pressure is the one that's relevant. It's reading 2.8 kPa right now, which is essentially zero. It's just reading, it's as close to zero as you'll ever get. For this purpose, so the pump I'm going to turn on for a second. We'll very slowly open the valve to the top. And you'll see the pore pressure start to go down. I'll turn it off now. Put a negative pressure about negative 22 kPa on the sample. Negative 22 kPa is perfect because it's just enough to hold it steady, but not enough to be higher than the stresses we're going to use eventually in the test. It also, this provides a useful leak check for you because Triaxial testing leaks are a major problem. 5 valves in here, you've got membranes, and if there's a leak between the cell and the sample, it ruins your entire test. So the nice thing about this is you can apply the section of negative 22 and then leave it for 5 minutes while you're setting up. And if that doesn't go down, or if that stays negative 22, that indicates there's not a leak on any of these fittings. It just saves you a lot of potential time. Because if you don't find out about the leak until later, it's much harder to recover. So now I'm going to remove the split mold, because I think the sample now is going to be able to stand up in a good way. This part you want to be very careful with. You don't want to go sticking a screwdriver into the side of the sample. It could break the membrane or damage the sample. It now has a top platen and a bottom platen, a membrane, a latex membrane that enables us to have a different pressure inside the sample than outside the sample. The next step is I'm going to measure that sample dimensions because we need to know the height and diameter for all the calculations we're going to do in terms of stress and strain. So we're measuring the diameter of the sample. Now you got to be careful. Calipers, if you were doing this, are very sharp, so you have to be very careful how you bring them into contact with a sample. It's pretty regular, about 71.3. We're going to measure the height of the sample. We actually can't measure the height of the sample directly because that would involve putting these quite pointy things into an area. You really want to put them. So we measure the height from there to there, and because we know the distance of these other items, we can then calculate the height of the sample. It's a much easier, more accurate way to do it. I'm just going to record those numbers in the computer so I don't forget them. The next stage is check on the pore pressure to make sure it hasn't changed much from negative 22. Yeah, so it's gone from negative 22 to negative 21. That probably is not indicative of a leak because I've also at the same time been touching the sample, moving it a little bit. I'm pretty confident that's not a leak. What we need to do now is secure this system here so that they're not going to interfere with the cell when I bring it over top. Just a rubber band is usually sufficient. And then you can do a final little spin of this to get in a position that's most amenable to having the cell come over top. The cell can push on that because that's pretty flexible lines. That won't have any negative, that won't be a big issue. And this is a small little coupling we put at the top that enables the loading ram to dock nicely with the sample. Bring the loading ram away because we need a bit of space when we do the lifting. We tamp it in those 8 layers in a state of about 5% water content. When we do that, that means it enables us to target various densities easily. However, it's now in an unsaturated state because at 5% water content, a sand tamped like that will not be saturated. So one of the first things we need to do is saturate the sample to enable us to be able to do testing where we can measure pore pressure or volume change in a reasonable way. This is the Triaxial cell. This is what's going to go around the specimen, around the outer part of the specimen that lets us put water inside of here to apply pressure to the sample. So first we're just going to lift this cell onto Triaxial. Now this room that we're in, I should mention, was actually set up specifically to run this lab with all of you, but unfortunately we couldn't. This is the first time we've ever had it set up for this, but we can't obviously do it in person because of what's going on. First step is to put the Triaxial cell over top of the specimen. Line up the bolts. This is a relatively modern Triaxial cell. It uses water to apply pressure. Some more historically compressed air was used more often, and compressed air is not as good. It's less reliable and it has some issues with safety because compressed gas is much more dangerous if there's a leak or a release than compressed water. So we like to use compressed water. And it's nice that these new cells you can actually see the sample, which is much better for a teaching environment. So this is a reservoir of water we have that enables us to fill the cell with water. So what is going to happen is this cell is now going to fill with water. That water is very useful in that we can then apply pressure to the sample using water pumps. The test is controlled largely by these two water pumps, one of which applies pressure to the cell water, the exterior, and one applies pressure to the interior, the sample. So by having different pressures in those two pumps, we can consolidate the sample to different amounts of stress. So while that's filling, I'm just going to make sure this is tight. I'm now going to bring this loading ram here is what's actually going to can apply a deviator stress to the sample. So it enables us to apply an additional load vertically than is being felt horizontally by the sample because of the water. And that's how we shear the sample. Pushing this down causes an increase in sigma 1, where in a drain test, sigma 3, which is the horizontal stress, stays the same. So by increasing sigma 1, or the ratio of sigma 1 to sigma 3, we can cause the sample to fail. For example, in a drain test, which is what we'll be doing. So I'm going to bring this loading ram down because I need to bring this into contact with the sample in the beginning of the test, because that enables us to do things like track the change of height of the sample as it saturates and consolidates. First we bring this down, and then I open up the software. Now the software, there's no need for you to learn every detail of the software. The main thing is it's a computer program that enables us to control the test. It's really useful in that it can be done in an automated way, so you can run things overnight or a weekend and track the data very accurately. It's just what you'd expect for this kind of system these days. So I'm going to lower this shaft down. If you look closely, you'll see the loading ram coming into, or almost into contact with the sample. So now the sample is what we call docked. Having it in that position is useful, and then from now on we can track our displacements from that point. I'll bring the loading ram down. What I'm doing now is I'm lowering this very slowly while watching the load on the load cell within the cell. I want it to be docked very well to the sample, but I don't want to put too much pressure on it. That's now secured. This device here is called LVDT. The main thing is this measures displacement. So as this moves up and down, the computer can track what that displacement is, which helps us know the height changes of the sample during, for example, saturation or consolidation or shearing. Right now, however, it's not in contact with anything. It's just hanging free. So we need to adjust this so that it's touching the top of the cell. Then, once the test proceeds, we'll be able to track displacement. And by setting it right now to a 0 value, we'll have that'll be the 0 reference point for the test. Because we know the initial height of the sample, because we measured the sample as we prepared it and set it up. Now we can set this LVDT to 0 right now, and that becomes our frame of reference for the test. Just tighten that. And I'll go to the software. I'll just quickly 0 the LVDT. So these are two pumps that we use to control. This controls the cell, the pressure within the cell. This controls the pressure within the sample. So I'm going to currently just use this water reservoir, this bit of water here, to fill the cell pump, because we want to have that be full of water for this test. The back pressure looks like it's at a pretty good amount, and we don't need to adjust that water. We finished filling this cell with water. So now this cell is completely full of water and it's sealed at the top. The axial displacement's been zeroed as we suggested, and now the cell pump is full of water. The cell pump is full of water, which allows us to run the test without worrying about running out. So I'm currently going to turn this three-way valve around, so the cell pump is now connected to the cell. And now I'm going to apply a small amount of pressure using the software which controls the system. So this is the control software that lets us control the cell pressure, which is the pump outside of the sample, the back pressure, which is the pump that connects to the sample, and this panel controls what the load frame does. In terms of, does it move up, does it move down, or does it try to maintain a constant load on the load cell? So that controls the vertical direction of the system. So we're going to ask for a cell pressure of 40 kPa. We're going to tell the back pump to do nothing. We're going to hold the back pump. So the back pump is not activated at all. The reason we're doing that is all the things that we're going to do to the sample are going to cause it to get smaller. And if we don't have that kind of setting in here, and we're going to tell the load frame to keep a very small bedding load onto the sample of 0.01 kilonewtons. Very little, that's maybe 1 kPa of deviator stress. What will happen is the sample will get smaller, but the load frame won't move, and it will disconnect from the top to the sample. We don't want that to happen. We want this top to stay in contact with the sample throughout the process so that we can track displacement. And that's why we need to put that setting in that panel. This is the control system that lets us see graphs of what's happening. Start the test. You'll hear the pump making a pretty minor noise. The pump is now trying to achieve the 40 kPa that I asked it to do. I'm now going to open the sample to the atmosphere, because the sample has been sitting in there under a suction of about 20 kPa of air pressure. The reason I'm doing that is I don't want the pressure on the sample to come too high. So now the sample within the rubber membrane is connected to the atmosphere, so it's at about 0 kPa, whereas the external water in the cell is at about 40 kPa. So it's being confined, it's being consolidated very slightly to 40 kPa. This is much lower than what we're going to be testing at, but it's just a good initial value to get us set up for the test. The next thing we need to do now is saturate the sample. Now we're going to do that by flushing water into the bottom, slowly, allowing it to expel the air within the sample, which will then come out and exit the top. One of these pieces of plumbing is connected to the top of the sample, one of them is connected to the back. So we're going to take this reservoir of water again. That header tank is probably under about 10 or 15 kPa based on the elevation compared to the sample. So that 10 or 15 kPa can now go into the bottom of the sample, causing the water to leave. In order to track that process, we're going to put the top drainage valve into a cup. That way when water is being expelled from the sample, we'll see bubbles emerge. I'm now going to open the drainage valve to the bottom, allowing that water to start percolating through. Now immediately, you're going to see bubbles coming out the top. Those bubbles represent the air within that sample that's being expelled by the water from the header tank. At that stage of the process, we're just going to leave for about, 15 minutes or half an hour. So you can see the bubbles still coming through. That means it's still saturating. This process can take an hour or two, so we're not going to show you a video of the entire thing. What we're going to do is send you some photos and data for different stages of the test that you can use in your interpretation.